Hi, my name is Guy, and I will give a short presentation on probabilistic indistinguishability and its use in analyzing the quality of the validity property in Byzantine Agreement. This is a joint work with Sasha Spiegelman from Novi Research and my advisor, Yoram Moses. Lower bounds and impossibility results are a major part of distributed computing research. They are both intellectually challenging and practically important. The notion of indistinguishability has for years been one of the most useful tools in proving such results for deterministic protocols. I recommend Naama's Jam session from the recent PodSig on the topic. These deterministic lower bounds typically rely on the fact that if a correct process cannot distinguish between two executions of a deterministic protocol, that is, its local state is the same in both, then it performs the same actions in both. In a randomized protocol, however, the fact that two executions are indistinguishable to a process up to a certain time does not mean that its next action will be the same in both. Also, an execution by itself does not provide information on the probability with which actions are performed. So, what tools do we know for proving lower bounds for randomized protocols? Actually, there are much fewer lower bounds for randomized protocols when compared to the abundance for deterministic ones. I'm talking about the asynchronous communication model, of course. Typically, when such results are proved, it receives considerable acknowledgement and involves non-trivial arguments. Good examples are Hagit's and Karen's outstanding work that have used delicate ad hoc structures in order to use deterministic indistinguishability arguments while still accounting for the necessary probabilistic information. Unfortunately, these rigorous structures are not easy to translate into other problems. That is where we come. By generalizing the notion of indistinguishability, we provide an intuitive yet rigorous framework to reason about randomized protocol. Our notion of probabilistic indistinguishability makes it easy to use arguments that are very similar to the deterministic case, only that now one claims indistinguishability between sets of execution instead of between the executions themselves. This notion naturally generalizes indistinguishability so that it captures the probabilistic information as well. In order to make any probabilistic statements, we first need to define our probability space. This is naturally done by gathering into a set all the executions that correspond to a given strategy that might be chosen by the adversary, and defining a probability space over this set. This can be represented by a purely probabilistic tree structure in which the nodes are global configurations and the edges are transitions and their probability of occurring. Let's call this structure an ensemble. It is analogous to the common definition of an execution as an alternating sequence of configurations and transitions. Just like in the deterministic case, an adversarial strategy and a protocol define an execution, in the randomized case, an adversarial strategy and a protocol define an ensemble. Next, we define an iLocal ensemble based on an ensemble. An iLocal ensemble captures what the ensemble looks like from I's point of view. I've prepared an example to explain the definition. Here we have an ensemble. Each node is labeled by a distinct configuration, the CXY label. The transitions between configurations might be probabilistic. For example, in the initial configuration labeled C0, the adversary schedules some process, say J, to act. J's protocol triggers it to flip a coin with probability 0.4 getting heads, which leads to configuration C11, and 0.6 for getting tails, which leads to configuration C13. If the configuration C13 is reached, the adversary schedules process I to move. In this case, I's protocol prescribes that I rolls a three-face dice with probabilities 0.3, 0.2, and 0.5. For explanation purposes, I've colored each node based on I's local state in that configuration. For example, I's initial local configuration is blue. And after rolling a dice at configuration C13, it transitions either to the yellow, to the pink, or to the red local state. Moving to the I local ensemble, we see that I's initial configuration is blue, from which it transitions to red with probability 0.7, to yellow with probability 0.18, or to pink with probability 0.12. I think the rest is self-explanatory by now. The main benefit of generalizing the concept of a local history into a I-local ensemble is that it keeps the essence of the execution local history relation. Defining the probabilistic notion of indistinguishability then becomes completely analogous to the deterministic notions. Two ensembles are indistinguishable to process I if it has the same I-local ensemble in both. If you remember, the deterministic case just said executions are indistinguishable to I if it has the same I-local history. So we get a very natural generalization of the indistinguishability notion. When we take a closer look, we can notice several nice properties of this definition. One, it has just enough structure, which means that it does not require anything stronger than necessary. For example, you can see here that there isn't a one-to-one relation between the ensembles. In fact, one ensemble contains 7 executions while the other has only 6. This is because the I-local ensemble structure explicitly describes the relevant probability space on I's perspective of the ensemble. Also, the projection from ensembles to I-local ensembles can be efficiently computed, although it requires combining different nodes that might have arbitrary distances between them. In the full version, we give an explicit algorithm to do so. Another useful property of the indistinguishability between ensembles notion is that it enables to directly translate the concept of an indistinguishability chain among executions to an indistinguishability chain among ensembles. This concept of indistinguishability chains is very useful in proving lower bounds on agreement problems, which is another indication that this generalization is a good one. The notion of indistinguishability between ensembles clearly accounts for systems with infinite executions as well as for randomization sources with an infinite range, as long as the range is countable. For example, here we have a randomization source with a Poisson distribution. Right? This is also infinite but countable. This means that this framework is very general and more or less supports anything that can be reasonably expected. We're done talking about indistinguishability and focus instead on Byzantine Agreement. Byzantine Agreement is a very interesting problem in the field of randomized protocols. Randomized Byzantine Agreement protocols form the core of many blockchains, and using randomization also allows to tolerate asynchrony. As blockchains spread in number and influence, there is a growing interest in the fairness guarantees that a blockchain provides. Loosely speaking, we ask, what is the probability of a Byzantine Agreement protocol choosing a good value? This is sometimes called chain quality. We say a value is good if it originates from a correct execution of the protocol, meaning that it was not invented by the adversary, but it was prescribed by the protocol. However, corrupted players can lie and send different values from what the proposal mechanism prescribes. We consider optimal resilience of up to third corruptions. Or in other words, we look at the classic asynchronous model with Byzantine faults, where the adversary is computationally bounded, which enables the use of cryptographic primitives such as signatures and the hash functions. The problem's interface is such that each player starts with some value from a large domain. This is the value the player should propose, but a faulty player can lie and behave as if it has started with any other value. The output of a process is a decision value, and the protocol that solves Byzantine Agreement must satisfy the following properties in every ensemble. First of all, agreement. The decisions of honest players are the same. Termination. Since deterministic solutions are impossible, we consider a common approach that never compromises safety and provides termination almost surely. That is with probability 1. As for validity, since we care about the multi-valued Byzantine agreement, there are two common definitions. The first is the classic weak validity definition, and the second is external validity. The weak validity definition originated from the binary case. It states that if all honest players propose the same value, then that is the only valid decision. However, if honest players propose different values, then all bets are off. Usually, in the cases where it is not clear what to decide, a predefined no operation is decided upon. This definition is somewhat problematic for a blockchain system, as it requires an a priori agreement in order to achieve meaningful progress. Opting for the second option of external validity does guarantee progress. It is commonly accompanied by a quality condition, for example, with probability half the decision is good. But this definition allows the abnormality of deciding on a bogus value even if all players agree a priori, which is clearly not a desired property. We formulate a validity condition that generalizes both weak and external validity under the same rules. Qualitative validity gives an adaptive guarantee based on the actual ensemble we are in. It can be read as if at least 2t plus 1 honest players start with the same value, then this value is decided. Otherwise, the probability of making a good decision is at least 1, minus the actual number of failures divided by the number of players minus the maximal corruptions tolerated. In the paper, we show that nothing better than qualitative validity is achievable, even against a weak and static adversary. Weak in the sense that it does not observe the local states of the honest players, and static, meaning that it has to decide who to corrupt before any message is sent. Proving this claim was greatly facilitated by the notion of indistinguishability between ensembles. Using this framework provided us with a rigorous proof that is also easy to follow. In the paper, we also show that this bound is tight by showing a protocol that achieves it. To summarize, indistinguishability is a basic building block for proving the limitations of distributed algorithms. We have defined a notion of probabilistic indistinguishability that generalizes its deterministic counterpart. This is not the only possible generalization, but we feel it is a useful one. We use this framework to analyze the limitations of asynchronous Byzantine agreement protocols. Specifically, we've focused on the essential validity property, which relates to the probability of making a good decision. We've introduced qualitative validity, a new and probabilistic validity property for multi-valued Byzantine agreement, and finally, we've proved that it is impossible to satisfy a validity property that is stronger than qualitative validity. There is still much more to be done in the sense of providing formal tools to analyze asynchronous distributed problems. For example, notions of similarity rather than distinguishability, that is, ensembles that might be distinguishable yet appear to be very similar. And what effect does similarity have in comparison to indistinguishability? Also, accounting for correlation between different players' local states can lead to interesting notions. I thank you for your attention, and we invite you to read the full version on Artscape. Thank you.